Today, I'd like to share with you some of my work over the last 2 decades through these 4 projects. One is the Mars Home design for a first settlement on Mars that started as my Master of Architecture thesis, and I worked on it for a couple more years with the Mars Foundation. The surface endoskeletal inflatable module, which I worked with Constance Adams, one of the pioneers of space architecture and one of the best space architect designers that I've had the pleasure to work with. Fortunately, she passed away a few years ago. And then the 2 projects with Skidmore, Ranks and Merrill, the Moon Village, which Sandra mentioned, and this new one with a collaboration with Lockheed Martin. But I don't want to just go through a bunch of projects and say, here we did this and here we did that. And I've always liked talking about ideas in space architecture. And we actually got a really beautiful opportunity to do this last year. We got invited to participate in the Triennale that also Sandra mentioned by Arcilia Valdo, who's the curator. And she challenged us at SOM to develop a decalogue for space architecture. Basically come up with 10 ideas or 10 issues that every space architect has to address and somehow represent them at the exhibit. So together with our partner here, Colin Coop, and our writer, David Vanderhoff, we sort of wrote as succinctly as possible these 10 ideas for space architecture. And we worked with this company called ... who gave lovely vision to our text without suggesting any design. So we were trying to just talk about the issues without saying, like, this is what you should do, but it's more about what you should think about and then come up with ideas. And so the Triennale ran until last month. Unfortunately, it's finished. It was pretty successful, and we hope to bring this exhibit again. But today's talk, I'd like to go through some of these ideas and show you how we've addressed it in different ways. So the first one is gravity. The human body has evolved in 1G, but as we go out into outer space, we can experience different forms of gravity. Extra G's at liftoff, microgravity, 1G on the moon. And these are kind of like the 3 main destinations that we've all, space architects, thought about. Low Earth orbit, which we have a lot of experience with, the moon, which we have some experience with, and Mars, which is only experienced by our robots so far, and I'm hopefully one day humans as well. And each of these spaces has a different type of gravity. In micro G, where in Earth orbit, you're kind of falling with your habitat, so you have this perception of weightlessness, which is a lot of fun, but it's also very detrimental to a human body. So our astronauts spend a vast amount of their time exercising and trying to prevent the degradation from the microgravity. Space architecture has been imagined for a long time of how you could combat that, right? One idea is to spin the habitat around and, produce artificial gravity by von Braun, 2001 Space Odyssey, O'Neill settlements. In reality, this has not come to pass, and it probably won't come to pass for a while because of the vast amount of matter you have to bring up to low Earth orbit. More realistically, you would probably use the rocket as a counterbalance and just spin your habitat around. And the wider you make, the longer you make the radius, the more gravity you could get with the lower spin. So these are some ideas being explored by space architects of how to create artificial gravity. But once you get to your destination, you have to make sure everybody survives the harsh habitat. And on Earth, if there's an issue with a part of our building, our codes, our architects, the goal is to get everybody safely out of the building. If you're on the moon or Mars, chances are that the outside is actually more deadly than any emergency you would have. And so your habitat has to be resilient in a sense that if there's any issue with one part of your structure, it should not separate or cut off the rest of your habitat from the livable parts. You can't have any single point failures. It should be efficient and easily expandable because we hope to create long-term settlements, so not just one-off visits to our destinations. And so we've worked at a lot of different precedents in looking at how humans have been constructing new habitats on Earth for a long time. Grids are popular systems. There's the law of the Indies that was designed basically out of Madrid that would be applied to all cities and colonies founded by Spain. So if you go to Latin America, a lot of the old cities have this grid line with the Plaza Mayor in the center and the church and the governor's house and a radio grid coming out of there. In the United States, also west of the Appalachians, there was the law passed by Thomas Jefferson, the Public Land and Survey System, which basically divided all of the land that was acquired by the U.S. into these mile by mile squares that are further subdivided. And so, the Jeffersonian grid is another example. We looked at radial cities, Ideal Garden City by Ebenezer Howard in the Industrial Revolution. But I think judging them on all these criteria, this master plan idea of the linear city, first articulated by the Spanish architect Arturo Soria, made famous by Le Corbusier, is kind of a very appropriate for outer space. It was an idea of how you could grow cities around all of this new technology and transportation and infrastructure that was coming out of the Industrial Revolution, and these bands of development that could grow and connect central points. Looking back at other space master plans throughout the years, you see this linear pattern emerge many times. This is a project by Guglielmo Totti with Buckminster Fuller here as an advisor. Brent Sherwood, who gave the previous lecture last month, had a project from the early 90s for a master plan on the moon, which again, the linear settlement. An Obayashi Corporation project for Mars from the 90s. And this is recurring in more recent student projects from a few years ago, and this one was published just last year. Again, this idea of having linear bands that are interconnected together. So I explored this first on the Mars Home project, and we did have this double band pattern that could expand in each direction, interconnected as often as possible. And then we arranged all of the program, all of the different spaces along these two bands. And so the part of the idea here was that one of the bands would be buried under masonry structures where the pressure is balanced by the overburden that deep in a hill, and then a series of pressurized elements kind of reaching out towards the surface and having access to the vacuum outside on the surface. Here's a section of the two bands going in and out of the page. And if you have your design, it's really easy to keep expanding and replicating this pattern around. In this case, we decided to do it around this hill. For SOM's Moon Village project, we again started with our location on the South Pole. And probably most of you in the audience are familiar why the South Pole of the moon has become so interesting in the last few years, because of the availability of light and the availability of probably a lot of interesting frozen material in the permanently shaded craters that are both interesting scientifically and interesting because they're a usable resource on the surface of the moon. And so on the South Pole is dominated by Shackleton crater, which is pretty massive and deep, But along its perimeter, there's actually a lot of smaller depressions that are also permanently shaded. It could have very interesting material scientifically and exploration-wise, but also much more accessible than the deep crater. And so we laid out our master plan in these bands. So first, a habitation band where all the habitable modules would be, and they're positioned along the perimeter, looking both into the crater but also out. Then we proposed an infrastructure band where all of the power generation and all of the external life support systems would be housed. And finally, an activities band. The idea for the Moon Village was that you would take the precedent of the International Space Station, where instead of each country competing together, there is a shared infrastructure in which each country or entity could tap into for their needs. So for a moon village on the moon, for example, you could have a government organization preparing to do a long-term exploration and could use part of this activities band to stage their long-term exploration. Next door, you could have a tourist company that is, providing sports and entertainment activities outside on the moon. And so this idea that we share the infrastructure, but you could have many different activities taking place at the same time. And then you could expand the bands along the rim in the future. We tried to work out in more detail, zooming in and how the different bands would be laid out. You can see here the pattern here of our modules, not entirely complete yet. And a rendering here showing the habitats. The crater is at the top in this view, and then the other two bands are along the bottom. And you can see precedents like this on Earth. This is the Amundsen Scott South Pole Station, and you see the original station from the 60s of the dome on the left, and the new station from about 10 years ago, expanding in a linear fashion, and you have a neat arrangement of your construction material, everything laid out in neat zones. The other precedent, though, from Antarctica is McMurdo. This is the biggest settlement in Antarctica. And although it is efficient, it's kind of laid out very haphazardly without any sense of place. And we wanted to have this idea that a master plan shouldn't just keep everybody alive. It should make them proud to be there. And every city on Earth has this moment, right? Usually around parks where you can show the image and you instantly recognize where it is in New York. Same for Vienna with the Ringstrasse. It's a sense of place and identity for the city. And so we were thinking that for the moon village, a good idea would be to leave a bit of the moon as pristine as possible, untrampled by footprints or tracks or infrastructure. And that would be the image that would be shared by the moon village. And we decided to position it in a way that is facing towards the Earth. If you know, on the moon, because of the orbit and because it's locked, as you're standing on the surface of the moon, the Earth is always sort of hovering in one space on the horizon. Throughout the year, it sort of wobbles a little bit back and forth, but there's only one direction where you can see the Earth. And so we thought this would be a poetic gesture to put the pristine lunar park in a way so each of the habitats can look at the Earth through this pristine, uninterrupted part of the moon as well. Now that you have your settlement planned, you have to deal with the fact that everybody's going to be living mostly inside. And on Earth, we have a variety and richness of spaces in our cities and daily life. We have places for one person to be together, to be alone, one person to meet with somebody else, small groups to meet together. And then we have spaces for the whole community. So you have to balance this need for communal life and absolute privacy. and you have to deal with it with very little space. This is the Soyuz spacecraft. More modern spacecraft have a little bit more space, there's these historical graphs of how the longer duration you plan on spending, the more volume you need per person for a successful habitat. But it's not just volume, it's the type of space that is very important for a space architect. And this is the diagram from the Mars Home project, where we highlighted places where a crew member can be alone, where two crew members can meet, where you can have small groups meet together, and then you have to have the place where everybody to come together. And this is kind of what happens on the ISS. There's the personal quarters where you can shut yourself off, at least visually. But there's the iconic image around the table where the whole crew meets together and is photographed for parties and events and human gatherings. This one's from Mir, an earlier. And again, you always see these pictures of the crew at this around the table. The other very important part about dealing with confinement is the view out. You have to be able to see outside, and making windows is extremely hard from an engineering point of view, but extremely important from a design and human point of view. And the cupola of the ISS has really become the icon for this, the place where you can really go out and experience the world outside of your habitat. Another bit that must be considered is this idea that a space habitat should really be an ecosystem involving humans and other species. If you look at most of our science fiction images of space, it's always humans and their machines going out to take over the universe. And the keen of you will notice, well, Georgi, this is all sort of military and exploration vessels. But if you try to dig up science fiction images, it's never populated by other species unless they're the enemy. It's always humans and machines. And this is kind of the case we have right now. This is the life support system on the ISS. It's all a bunch of equipment that is trying to close the life support system, closed loop as possible, but it's all machines. They are projects trying to introduce biology into this loop, and the Melissa project by ESA is one of them. But besides the life support, plants are really integral to human well-being. In the last few years on the ISS, we've seen every time they have an experiment with some kind of plant, the moment where they harvest the product is a moment for celebration. You get a sense of accomplishment. You get the smells, the feel, the fresh food. So the integration of plants into space habitat is a very, very vital question. On the Mars Home project, each of these spaces that I told you about along our master plan also had an idea of how to integrate greenery into it, whether it be the crew quarters or the gathering spaces or the greenhouses. We even had this idea of the first tree. So you would plant a tree that would keep growing with the settlement, and as new people arrive, they would have their picture taken at the first tree as a symbol of the growth of the settlement. So you can come up with various interesting ideas of how to integrate plant life. On our Moon Village module, because this was an earlier stage, we designed the sort of the first module. We had an experimental greenhouse as part of one of the levels. Color is extremely important too. On Earth, we have a rich variety of color of the natural habitat, and it changes through the seasons and throughout the year in most places on Earth. Our main destinations, the Moon, is predominantly gray, but even Mars, even though it has a color that's not gray, it's still one color almost everywhere. And so in our latest project, we tried to introduce a lot of textures and earth tones in both the public space and the crew quarters. You know, maybe an important part of this color scheme is to let each of the crew members customize the colors in their habitat, and maybe they could change and not be static. So on the ISS, is, you know, color is not a big driver of design. You know, there are moments like these from a few years ago where they had a celebration with a splash of color too. But the introduction of color and thinking about how it could be both emotional but also orientation, helping with the orientation is very important. Light. On Earth, we have a single day is 24 hours. On the Moon, you know, we have the cycle of 12 days of 14 days of light and 14 days of darkness. On the South Pole, you do have an even weirder combination of large stretches of light, but also strange periods of darkness. And this is very important for humans, the change throughout the seasons, but also change of the light throughout the day. On a typical Earth day, we get a lot of different conditions. On the ISS, the lights are on or off. And so for our Moon Village, we partnered with a lighting design company here and coming up with this idea of you could wash the walls in different types of lights. So in the morning, you could start with warm light at the bottom. Throughout the day, the lighting strategy could change where it's more white light coming up from the top as people are active. You can cycle back to a sunset, warmer, taller colors in the evening. We do also these, you know, quite complicated studies to ensure not just the quality of light, but the amount is appropriate for each of the tasks or each of the public spaces as well. This is from our Lockheed Martin collaboration. Another important bit is basically radiation. The universe is out there, is a dangerous place, and it's trying to kill you all the time. On Earth, we're protected by our atmosphere and our magnetic field. Anywhere we go in space, it would have to be the architecture that protects us. And there's low-level radiation from cosmic rays and solar wind that are constant. And then periodically, our sun throws out a big solar flare that is a short duration, very high dose of radiation. But fortunately, it's predictable. We have space weather, and you get about an hour's warning for this. And so, you know, some of the strategies are burying the habitat with regolith if you're on a surface. More recently, you know, examples like this from Hassel show you a 3D printed shell that would protect your habitat while also allowing views out. It turns out that hydrogen is a really good element that protects against radiation, especially materials that are high in hydrogen. And one material that is high in hydrogen that you have to have anyway is water. And so there's this very cool project trying to integrate the water cycling system of your habitat. Instead of it being a machine that's stuck in a corner, what if it's this thin layer that could coat the inside of your habitat? And this was Mark Cohen, who is in the audience, one of his very cool projects. So there's other ideas of how to put hydrogen all around the habitats. This is one from Search Plus, where they propose 3D printing a ice shell around the habitat. In our Mars home, we kind of placed most of the habitat buried deep underground. And so on Mars, you need about 10 meters of soil to balance the pressure and internal pressure. And so that was used as the protection. For our Moon Village project, there was a detailed study by some our collaborators in ESA where they took our habitat and made a radiation model out of it and proposed several strategies. One is kind of partially burying the habitat. The other was this idea to have a protected part of it. And so on the South Pole, as we've talked, the sun is always at the horizon. So the solar flares would, all of the radiation would come out at you at the horizon. And so if you take the lower level of the habitat and provide in this case, we proposed a 3D printed wall around it, then this could be your shelter where the crew could hide for the 1 hour or so it takes the solar flare to pass through. Another important thing is mass. Transporting molecules from one gravity well to another is very energy intensive. And so this is probably even one of the most stringent drivers for space architecture. And you know, the legacy here is that everything that sort of started flying in space originally was really the top stage of a rocket. And in the case of Skylab, it really was the last stage of an unused Saturn V that got remodeled into the space station. But you know, you have to fit everything that you're designing into the fairing, both the volume but also the mass requirement of the rocket. And so all of your designs that for whatever you plan on putting on your rocket, you have to really think about it, how it will fit in the fairing, how it will be fit into the adapter, and measure all of the mass as well. This is the rendering of how our Moon Village habitat would fit inside of a fairing. This is it folded in. You also have to think not about just the rocket to get you to low Earth orbit, but also how you will get to your destination. And here we wanted to maximize the size of the habitat that would fit, which means that the actual transportation system would have to be something else. Generally, as a rule of thumb, if you want to put something on the surface of the moon, your lander that takes you from lunar orbit down to the surface would be probably half the mass and half the size of, or as big as the object you're trying to bring down, so half of the total. So for our Moon Village proposal, we had this idea that the habitat itself would have no propulsion, but would go to low Earth orbit, be picked up by a lunar transfer vehicle, which would shuttle between the Earth and the Moon and take it to lunar orbit, where it would transfer to a lunar lander who would bring it down to the surface, and then it would get picked up by one of the rovers with a portable crane and bring it to its final destination. You know, another cool idea is the sky crane that got pulled off twice now on Mars, where you basically have a lander with the rockets that comes down, hovers over the surface, and gently lowers your payload down. There have been ideas of how you could do this, you know, with a human-rated habitat object as well. From our SEAM project, here we had a basically you land somewhere all folded up, and then you bring it with a unpressurized rover again to your base that is growing. There are, you know, two ways that people have thought about of putting things in rockets. There's the rigid modules that basically all of the ISS is made out of, that were made to fit inside the space shuttle or the Proton rocket. Or there's this the precedent of Transhab. You know, this was a design that Constance worked on back in the 90s with another space architect, Chris Kennedy. You know, the idea is that you have a rigid central core which takes all of your loads during launch and transfer, but once you get to orbit, you can contain the atmosphere with an inflatable shell that comes out. You know, this is a precedent that's inspired a lot of work and a lot of space architects. that was tested to full scale. This is at Johnson Space Center, and how it would inflate. In the last 10 years or so, the company Bigelow Aerospace has taken this idea and developed it further with some large-scale mock-ups. They do have currently, it's right now attached to the International Space Station, a sample module that's mostly used for, I think, storage right now, but also as a test of the technology. And in the last 2 years, Sierra Nevada has really taken up the flag and pushed the technology even further with full-scale mock-ups. And recently they had two engineering mock-ups where they inflated it until it exploded. So I recommend going to see those. In my experience, my first attempt at developing new ideas was to take this, the TransHab, and try to adapt it for a surface condition. So the TransHab is in a vertical configuration, and Constance and I worked on how you would take this and adapt it for a horizontal configuration. So here's all of the rigid elements packed together during launch. And when you get to the surface, you could fold them out and create your walls and panels and floors. And then we spent some more time afterwards optimizing the shape of the inflatable. And this was how we were imagining growing a settlement out of these SEAM modules. But from an architecture point of view, how is that important? Well, if you have a rigid capsule like the ISS, you have the fairing of your rocket, and then you have the shell that contains your pressure, and you're basically architecturally left with a cylindrical monospace, which a lot of people have thought about how to deviate up this space, and there's a lot of creative ideas, but this is what you get. On the TransHab idea, you have the rigid central bit, and then when you go to space, you inflate your pressure shell, and then the architect, you have this sort of torus space that you can work with. And so for the Moon Village, we thought, well, what else can we do that's possible? What if you put the central rigid structure that's carrying your loads during launch and integrating your life support system, put them on the perimeter and inflate 3 shells from there, then you would free up the central space and you would have one continuous space that's a lot bigger to work with. And so this is kind of what we did for our design. We have this 3-part T with 3 shells and a big central space on every floor. We divide it into 4 floors in this case, a workshop, a lab, a crew quarters, and the garden that I mentioned. Ideas that as you grow the settlement, you would start specifying different programs for different modules, just like you do on Earth, right? You have different buildings for different functions. We decided to concentrate on the design of the first one, and by definition, the first one has to have everything in it. But we were envisioning later on that you would get one of these that would be entirely your lab, and another one that would be entirely storage, another one that would be entirely crew quarters, and so on and so forth. Here's the section of the 4 floors that we laid out the space on, with the circulation through the center in this open space that's continuous. We also thought about how you would fold out the floors and worked quite a bit on trying to come up with the correct geometry for the shell, because it's this 3-part Part T required us to have a quite more complicated geometry for the inflatable shell. Another consideration that I've alluded to is the extremes in both temperature but also pressure. And how you contain the pressure is important. And we have this classification of space habitats that was, I think, invented by Mark and years ago. Basically, class 1 is pre-integrated, everything is ready to go, and you send it to your destination. Class 2 is modular elements like Mir or the ISS, where you build them slowly over many different launches. And finally, class 3 would be habitats built using materials that you find at your destination. But in all of these, the main force that you're trying to deal with is the containing the internal pressure, because most of these destinations practically, for all practical purposes, vacuum. And just to give you a sense of scale, you're probably sitting somewhere on Earth on a floor, and usually we design these floors for 2 to 10 kPa of pressure of gravity. And depending on what kind of atmosphere you want to hold on your habitat, the order of magnitude higher is what the force is to contain the pressure. So the pressure at sea level is 100 kPa. And even if you decide to go with a lower atmospheric pressure than surface, the sea level, it's still enormously higher pressures. And so that's why you have these cylinders and oval and circle shapes that you have to deal with, because it's impossible, very hard to contain pressure as in bending in flat surfaces. You always have to take it in membrane action and tension in your shell. So when I first started thinking about space architecture, these were the things we could work with. There was a lot of precedence for pressure vessels, and people were thinking about inflatables. But there was also this idea of building with masonry and covering up the pressure by burying your habitat under the weight of regolith. And there's all these historical precedents of how you could build efficient vaults by leaning the arches, and you don't need any centering. This image on the left was really captivating for me by this architect Hassan Fathi, who was thinking about how to adapt this to outer space. You can also do domes. And so this was actually my first built space architecture project. I was one of the early crews of the Mars Desert Research Station, where the project I brought to my crew is to try to build a vault. So you see here, we're collecting our material, the in situ material, local materials. We have our pressurized rover that we use to carry the material around. And then in simulation spacesuits, we built this vault. Here is the final product. This is my first structure after graduating. But all joking aside, here's you have your class 1 habitat that you brought from Earth, and you're trying to build your class 3 habitat out of the local resources. In reality, laying bricks with spacesuits is not the right way to do it. One idea to make it easier is maybe you could have a pressurized construction tent that at least you could work with in shirt sleeve environment and not in a spacesuit. But really, if you want to do stuff like that, you would not be spending astronaut time, which is extremely precious, laying brick. The analogy, I think more of it is the idea of a master mason who lays out the main course and sets the parameters, and then you have the apprentices filling it out. So the idea would be that the humans would be kind of guiding the robots, or at this point probably even automated, to create a habitat. And this is a project that we at SOM we did in collaboration with Princeton to see if we can get 2 robots to collaborate with humans to build a vault. This is another project from last year from UT Zurich, a student project, again, trying to come up with 2 robots cooperatively building a vaulted structure here that looks very much like it could go on the moon or Mars. But this was 20 years ago. In the last 10 years, additive manufacturing has really gained a lot of traction, a lot of interest, and there's a lot of competition that NASA has already sponsored of trying to figure out how we could use this technology in order to help us build in space. This is a project that we did at SOM with the Army Corps of Engineers to 3D print concrete. This was the winner of the first NASA 3D printing challenge, the Mars Ice House by Search Plus. This was their further iteration on the phase 3 of the NASA 3D printing challenge. This is another one by in collaboration with Icon, the 3D printing company. In our research, I think 3D printing it's hard because as you layer the material, there's inherently
Georgi,
Yeah,
we cannot hear you. Sorry, you're muted.
Your voice is on mute.
Okay, now it's working.
Okay. I apologize for that. How far back should I go?
It was just for 10 seconds.
Okay.
Not even.
Thank you. Give me a second.
And I think you have to share it again.
Yes.
Maybe for the audience in the meanwhile, we will go through your questions after the presentation. There will be room for a little Q&A.
Okay, I apologize. I was saying that containing pressure with 3D printed habitat is a tough challenge, but there's a lot of elements that you would need at a lunar or Mars settlement that don't require containing pressure. And one big target is the foundations for your habitats. You know, if your habitat is permanently located, it needs to get there once. It doesn't really need landing gear or wheels if you have something to get it to its final location. So the foundations, I think, would be something that's very easily 3D printable. Any also radiation protection and things like that. So this is kind of what we concentrated on as the 3D printing target for the Moon Village. But you know, we also wanted to explore 3D printing in steel. And if you think of welding, welding is kind of adding a little bit of molten steel. And if you attach it to a robot arm, you could 3D print steel. And so for our, you know, the Venice Biennale invited us to build a pavilion where you could walk into our Moon Village habitat. This is what it would have looked like. We kind of had to rescale it a little bit from a design for outer space to a design for an exhibit on Earth. But we partnered with MX3D, this company out of Amsterdam, who are famous for this 3D printed bridge. Here's the Dutch Queen opening it. And we decided to explore this technology for the floor. So this was one of the floors of our habitat with the 3-part diagram that I showed you with the structures, the vertical elements at the corners. And we used some of our form finding techniques to figure out where is the most efficient place to put material. Obviously, you can't take this result and just 3D print it. So you have to go through a few steps of rationalizing it. You also have to adapt it to the technique and the capabilities of the manufacturing process. So one of the criteria is that as you're laying molten metal, you can't have things that are more than 35 degrees off of vertical. So we had to kind of adapt the geometry to match that constraint. And then we have to really think about how the robot is going to build it, and whether our thing would fit within the reach of the robots. So we did a lot of studies and optimization of what the correct piece is, and how it would really be fitted with the robot. We also did a lot of structural optimization. There was different thicknesses of weld you could do. There's different speeds of the welding, different thickness, depth of their members in order to come up with the lightest possible structure. Finally, all the joints and how the branching happens during the 3D printing process. It's pretty beautiful material, and they printed it completely. Unfortunately, this bit was a victim of COVID, where our general contractor pulled out of us from at the last minute. But we did still have an exhibit at the Biennale. We had to quickly convert from the full habitat to a couple of models. And we did spend a lot of time putting together a video that was narrated by astronaut Jeff Hoffman telling our story. I will not play it for you here, but I think I'll let you have the QR code and look at it later. And with that, I think I'd like to finish telling my story and see if we have time for questions or conversation. Thank you very much, everybody, for listening to our story about space architecture.